I'm just going to give you a brief overview of feature selection and what this implies for machine learning. So the first question is what is feature selection? In other words, the main question we are trying to address in this process is which features should be used to create a predictive machine learning model. And this question is ever more relevant when we are discussing about multiple features, which is quite often the case in life sciences. So why do we need feature selection? So first of all, in most cases, what you do have is a relatively short number of data points, of records. The axis you see in the figure in the top right, and a big number of different features, of different variables that are used to describe these records. In this case, we have n data points and records and observations and the number of features. So in a lot of cases, data, raw data, can contain a lot of irrelevant, redundant, or unnecessary variables. And in a lot of these cases, actually have very few actual observations that you can use to train the model. And as you can understand, machine learning requires significant amounts of data to actually produce robust models. And when you're talking about datasets with tens or hundreds of thousands of variables, if you consider that every variable could be a particular gene, you might have in the human genome like 30,000 variables across 100 patients or 100 different cases. So this means that your n is in the tens or hopefully the hundreds, and the number of columns, the d, goes to a few thousands or even tens of thousands. So selecting the appropriate features, the most relevant features, is a process. So what is actually feature selection? So in short, feature selection consists of automatically selecting the best features for models and algorithms to be used, and to do that by asking the data itself. So these are the three major points. The first key point I would highlight is that we're talking about automatically selecting. Because if you're doing a manual selection, it's a completely different process, and also it's not easily scalable. Again, using the example of the 30,000 genes as variables, if you want to manually select some of them, it's possible, but actually doing a meaningful feature selection out of them is not really realistically possible. Selecting the best features is the keyword here is the best, because it also requires to have an understanding of what best implies. Best in terms of accuracy, best in terms of interpretability, best in terms of what. And also, feature selection requires to be able to ask the data itself. So it's not something that can come from an external process, but it's something that should be coming in from the data itself. So having expert knowledge of the application domain is actually quite important, because first of all, it provides better understanding of how the data is going to be used and what model that's going to be used using this data is going to be applied for. And also you have some intuition beforehand of which features may be useful to keep and which features can be safely discarded. So when we're talking about why feature selection, these are, this is, first of all, it's not my figure, so I cannot claim credit for it. And these are like the 6 major points for feature selection. I will try to go through them later in the next few slides. So first of all, the most key point is to actually remove features that are not relevant, not important, not useful. By doing that, you essentially increase the performance of the model, you increase the accuracy, you increase how well the metrics that we saw earlier actually work. Essentially, you also make your model more efficient in the sense that it's faster to train and it's easier to build. if you have less number of columns, a smaller number of features to use to train the classifier, it's going to run much faster. Also, by having a more a smaller number of features, would be also easier for you as an expert to understand what the model is about. And also from the developer's perspective, from the research perspective, it's going to be easier to debug. If you have problems, for example, if, for instance, instead of having 2 classes, you come up with 25 classes, like I did a few minutes before, it will be easier for me to figure out what I did wrong along the way. Looking at performance, this is actually an interesting point, and this is what it's called the curse of dimensionality. It's been shown that if you increase the number of features, after a while, the number of errors, the error rate is actually starting to increase. So there is a point, a minimum point, where the number of features actually is at an optimal in the sense of how much error they can introduce. So in other words, having a smaller number of features to use generally increases your performance rate. Additionally, if you have a lot of features, some of them may be relevant in the sense that either they don't affect the output of a model at all. So essentially, they introduce a computational burden, but that's the extent of it. But they can also have a negative impact in the model. So, for example, by introducing noise. An example here, again, not mine. It's you see on the left-hand side that you have a noisy less data set. And the classifier, the SVM boundary here, is a very clean line that easily splits between those 2 points. If you start introducing noise, you might start figuring out that this classifier, this model, is starting to deviate from what would be the optimal case. So having an appropriate selection of the features might also help you to create a more efficient model. Additionally, going beyond the performance itself, the accuracy, precision, and recall actually improve how fast the learning process might go. The straightforward approach here would be less features, fast run. But this is also another aspect, that fast run also means that you have less cost for measurements, you have less costs to store information, and you have less cost to compute. And even though in this particular set of webinars we're using Galaxy to run this, you might come across cases, and it means that computation is kindly provided by other infrastructure like Elixir, as well as the storage costs. It might come the case where you run this in your institutions when storage costs, computation costs, and everything else is something that you need to budget in for. So having a good feature selection process might also make your process, your project more efficient. An additional point here is the interpretability. And again, it's not necessarily in the terms of the actual feature might be interpretable, but also the model can be much easier for a single person, a single researcher, to understand what it implies, how it is structured. You have 25 features instead of 200 features. And I'm not even talking about having thousands of features. So having a simpler, a more robust, concise, and well-designed set of features for a model might help a lot in how this model can be used later on. Plus, it's going to be much easier to debug. I'm going to do a small sort of break here to differentiate between 2 different aspects that I've been consistently seeing as sort of used interchangeably sometimes. So this is about feature selection and feature extraction. So feature selection is essentially having a given feature set, So having gene 1, 2, 3, 4, 10, how to select a subset of them and go forward with them, the actual variables as they are. So out of the 10 genes, I select 1, 5, 1, 3, 5, 7, 9, right? So this is a selection of the given subset. Feature extraction is essentially producing a completely new set of features and select from there. So essentially, we're talking about the transformation of your original features into a completely different set of features. Those two can work together. So you can do a feature extraction. So by applying PCA, LDA, and SVD, you can create principal component analysis, linear discriminant analysis, or singular value decomposition. You can create a more appropriate set of features in the sense that these features now are better fitted to calculate, to provide predictive value to your model. And then from them, you can apply the feature selection process so you can select a subset of them, of these novel features. But these new features from the feature extraction process may not be necessarily interpretable because they're going to be a transformation of the original data, which might be the exact same one, but for example, normalized. But at the same time, they might be a combination of multiple features, multiple original features into a completely new single feature. So it's not easy to interpret what this relationship might be. So I wanted to highlight this here and spend like a few minutes discussing about it, just to ensure that what we are discussing now is this feature selection process, not the feature extraction process. So how to transform features to a different space. It's something I'm not going to be touching here. So this is what feature selection is about. So what are good features, right? So what would be a good selection? So ideally, we want to have features that are discriminative, interpretable, and representative. So I'll start by the discriminative in the sense that we need to ensure that we have features that ideally have different values for samples of different classes. And ideally, same values for the same classes. In other words, we want features that we expect to have a direct connection to your classes, because this will allow us to use them as part of the classification process of the classifier model. Moreover, we want features that can be easy to understand. If you have, for example, an expression is something that a human expert can understand. However, if we are talking about a combination of gene expression values, for example, 10 times the expression of gene 1 minus 0.5 times the expression of gene 2, and so forth. This is a combination that it's not something interpretable. It's not something that can be understood by an expert. And finally, we want something to be representative. So a feature that can be connected to the problem at hand, and therefore be a represented aspect of the final model. That being said, there are some caveats, if you like. So sometimes you might have a highly predictive variable, but at the same time may not translate in a very useful variable if you're talking about a multivariate model. So by having a single variable really predict a class or be connected to a class may not be very useful in the long run in the model itself. At the same time, a variable that appears to be useless may become extremely useful when connected to other variables, when used in conjunction with other variables. And finally, when you have two variables that are quite highly correlated, and in that case, you might want to get rid of one of them in order to keep the number of features smaller. Using them together may bring complementary qualities to the model itself. So in other words, consider all those aspects as things to consider, but not as strict guidelines. If this is the case, then do that. So putting this all together, how to actually do feature selection. These are some of the processes that take place, and you might recognize some of them. So first of all, eliminate features where you have high percentage of not really useful values. An easy example is missing values or values that you know that are noisy or that you know that they are really not something that you want to bring into your model. Another point and is to eliminate variables that you know that are highly correlated. So if you know that these are very, very strongly connected and they don't really bring something more, you can get them out. And using regularization techniques for statistics to actually ensure that all those variables are connected to each other or not connected to each other, you can group them and sort of identify what can be kept over. You can use algorithms out of random forest that we saw earlier to actually identify what is the optimal set of features automatically. And you can also use rather interesting statistic methods like the Borota approach to identify and run features based on their relevance. So yeah, it sounds like straightforward, but if you actually look at the feature selection, it's actually a model selection problem, and hopefully that is something that comes up after this discussion. It's not something that it can be straightforward. This is not a single solution, and it has been actually shown that it's an NP-hard problem. It cannot be solved in the polynomial time. So if you're actually looking for a unifying theory that says this is what you should be doing because this will always work, unfortunately, this does not exist. And an easy example to give you, if you have 20 variables and you want to select the best model, if you want to have an exhaustive search, you need to consider 20 models if you want to use each variable independently, then 20 times 19 divided by 2 if you want to use them by 2, plus if you do it by 3, and so forth. So this, if you calculate that, this actually gives you a million variable combinations to choose from. And this is 20 variables. If you're talking about 30,000 variables, you can hopefully understand that this is not something that you can do in a reasonable time if you want to have an exhaustive problem, which means, to connect to the first point, it's not easy, it's not straightforward to identify what is the best feature selection out of a set. If you look at the methods that are available for you, there are actually three main types. There are the filter methods, the wrapper methods, and the embedded methods. I'm not going to touch on the last ones because embedded methods are essentially cases where the algorithms actually have their own built-in feature selection process. The lasso regression case is one of those examples, so it actually includes a feature selection process in the classification in the machine learning approach. So the filter methods are essentially used as a pre-processing step, and the key point here is that they are independent of any machine learning algorithms. So in other words, they can be used in any pipeline that goes from data, features, model. Most of the filter methods are relying on correlation metrics like Pearson, Spearman, distance, and so forth, T-squared, ANOVA, Fisher score, and so forth. So all those hopefully ring a few bells if you've seen machine learning in papers or in other approaches. So essentially what they do, the filter methods, they try to run variables based on usefulness. So all those correlation steps or statistical tests, what they do is they try to see how you can rank all those features, all those variables based on an aspect of usefulness. They could be how much information they carry, how much correlated they are to each other, how much independent they are to each other, and so forth. The interesting thing is that they can use, as I said, as a pre-processing step, and they usually are quite fast. So they can, most of the algorithms that apply those filter methods, they are fast to apply. Also, because they are basically statistical approaches, they can be independent of the target variable. So you can use them regardless of if you're talking about a nominal class or a numerical value. And ideally, you can use them to infer or to get some insights of what the underlying structure of your features are, of your data are. So how to get the best out of them? Essentially, you can go ahead and identify what is your target variable, and you can go ahead and identify a binary target variable like high or low risk or control cases, high or low expression, or you can go and transform this to a numeric value if not possible. You can also try to focus on different subsets. So in other words, by identifying not appropriate, but organically existing subsets of data, like disease subsets or case subsets, you can see whether you can apply where different features are actually maintained throughout the different these subsets, which means that if it's a persisting feature, it means that it's actually a connecting upper aspect, so it might not help to use it as a feature, but it's something that's only evident in one of those cases, you can actually use it as a more relevant one. There are also a lot of different ranking techniques that can be used. Similar statistics are widely used in this case, linear models, decision trees, and so forth. And all those techniques have different strengths and weaknesses, as you can probably see. And another process that is occasionally used is to put in some extra variables and see if they actually have an effect. So in essentially, if you put some variables that are placebo, in the sense that I put some random numbers there, you want to ensure that your process actually filters this out. So it's mostly like a control aspect of your feature selection process. You want to ensure that random numbers, random features that you've intentionally inserted are actually left out. If they are put in, it means that you have probably something to figure out with the structure of the data itself. So going through the wrapper methods, and I'm not going to take much more of your time. So here it's the main process is to evaluate the variable based on the predictive power. In other words, create subsets of your variables, create models of those subsets, and see whether you have an increase or a decrease in the accuracy, in the predictive power of your model. Random forest is a good example of those cases because they essentially try to create different models based on subsets of features and see whether they can improve the accuracy. Wrapper methods tend to be embedded in the model processing itself. So random forest, as I mentioned, they actually do feature selection in the process itself. This is how they are designed. But at the same time, they can be quite computer intensive. I'm not talking about only the wrapper, the random forest, I'm talking about wrapper methods themselves. So ideally, you want to begin the process with a random number of variables. In other words, you can combine filter methods with wrapper methods in order to have a filter selection pipeline. These are some examples of wrapper methods. So linear models with cross-validation, other than the random forest. So here you have a random division of data in K groups, and then you try to see whether this can be improved by changing the groups to training one against the other. Another approach is to do the neural networks approach, so try to see whether you can identify relevant features from that. The problem here is that whatever is produced as an insight from neural networks, it's not actually something you can readily interpret because neural networks are not easily interpreted. So, and this is my final slide. What I want to highlight here is that there is no perfect algorithm to apply to the feature selection problem. It's essentially a key part of applying machine learning, and it's equally important, if not more, to the model selection because the features will directly have a direct impact on your model, on your eventual model. I've put some quick highlights here on the different feature selection approaches that they exist, but the punchline is that it's always good to keep it simple, which is following the principle of parsimony. In other words, try to maintain the simpler set of features that you see are relevant for your problem. If they work, it means that they are good enough to continue. And with that, I hope I gave you a quick idea of what feature selection is.